So this video is about the applications of convolutions and also a little bit about the intuition. So here's a direct application to what we've been doing, which is differential equations. This is a differential equation from a couple lectures ago. Partway through, we've taken the Laplace transform and isolated big Y of S. And then what we did last time was we used this property, the inverse Laplace transform of function times e to the negative something times s. We could use the unit step function and a shifted inverse Laplace transform of the other function. If this e to the negative 5s had been something more difficult, then we might not have been able to use this property. So the property we talked about last time is more general, where we're just doing the inverse Laplace transform of the product of two functions, and that gives us the convolution. So we're still going to call h of s this rational function, 1 over 2s squared plus 2s plus 3. We'll call g of s e to the negative 5s, and then the inverse Laplace transform of this function is the inverse Laplace transform of h of s times g of s, which is going to be the convolution of little h times little g, where the Laplace transform of little h is big H, and the Laplace transform of little g is big G. And if you did this, and then, so you do need to do a little integral at the end to calculate the convolution. But if you did all that, you would get the same answer that we got last time. So that's good. And then, of course, you can apply this to more general functions. A little bit about the geometric intuition of a convolution. So we're going to talk about this by looking at a pretty simple function. Let's look at the function that is 0 on the negative numbers, and then we're going to go up to 1 from 0 to 1. And then it's 0 again for anything greater than 1. And we're going to call this f of t and g of t. So two functions that both look exactly like this. Note that the area under the curve is 1. It's just that unit box. And we're going to talk about what is the convolution of f and g. Well, by definition, that's the integral from 0 to t of f of t minus u times g of u du. Okay, let's look at some cases. So first, in all of these, we're going to have to figure out what f of t minus u is. So first, we'll take t less than 0. Okay, if t is less than 0, then what are the important parts? The important things are f of 0 and f of 1, because before and after that is where those jump. So we need to look at setting t minus u equal to 0 and setting t minus u equal to 1 to figure out what f looks like. So t minus u equals 0 would mean t equals u. T minus u equals 1 means u equals t minus 1. Okay, so if t is less than 0, then we're going to have jumps at t and t minus 1. So that means for some value of t over here, let's actually take a different color when we're going to graph f of t minus u in this color. So we're going to be 0. We'll have jumps at t and t minus 1. T minus 1 is over here. So our f of t minus u will be that function. 0, 1 here, and 0 here. It's a mirroring and a shift is what's actually happening, but the mirroring doesn't really get shown because it's symmetric. Okay, so then what is this? Well, then the product, these guys are never 1 at the same time, right? At any value along the x-axis, one of these, the green and the pink function, is always 0. So this integral is just going to be 0 if t is less than 0. Okay. Great. What about t between 0 and 1? And it doesn't really matter if we include 1, but we won't because we'll include it in the next case. Okay, if t is between 0 and 1, then we still have jumps at t equals u and u equals t minus 1. So like, let's say t was a half, then we would have a jump here, and 1/2 minus 1 is negative 1/2, so we'd have a jump here. So we'd have this function. It would be 0 up to negative 1/2, or t, or t minus 1 is what this is actually. 1 here, and then 0 here. And so let's look at that combined with the pink function. If we multiply them together, as long as one of them is 0, we're down at 0, right? So we're down at 0 here because the pink function is 0. We're down at 0 here because the black function is 0. So we have this like little half unit square where we're not at 0. And in general, because that's really t, we graphed the t equals 1/2 case, we have a t by 1 rectangle where it's not 0. And so the area under the curve there is going to be t if t is between 0 and 1. Okay. Then what happens? Well, so as we let t go to 1, this shifts here. And then as we let t keep growing, we're shifting this way, and we still have some overlap. We'll have overlap until t is 2. So we'll go up to there. And then same thing, we got to look at where t and where t minus 1 are. So as we get bigger, like we might put t there, and then t minus 1 will be there. So we might get that square. And then we just need to look at the overlap again. So we'll have that part. What is, how big is that part? Well, t is greater than 1 now, so that length is t minus 1. So the other part of it must be 1 minus t minus 1. It's the whole unit square minus this part, because that's outside. So what does that give us? That actually gives us 2 minus t. And that's the length of the rectangle. The height is 1. So 2 minus t, if 1 is less than or equal to t is less than 2. Let's actually put 2 inside there. Doesn't really matter. And then our last case will be then if t is greater than 2. And then if t is greater than 2, this square will have moved along all the way past the pink one. There'll be no overlap again. So the convolution will be 0. And let's look at a graph of this function. So this is going to be a graph of the convolution. Let's see, we'll put 0, 1, 2, this way, 1, 2. Okay, so what happens? We have 0 if t is less than 0. We have t from 0 to 1. 2 minus t, so that would be y-intercept 2, slope negative 1. So what's going to happen is actually this. 2 minus t for t between 1 and 2, and then 0 here. And that makes sense, right? The overlap, the area gets bigger until it's 1, and then it gets smaller linearly. So we see this. This is the f convolved with g. And one thing to note is, let's look at the area under this curve. This is a triangle with base and height 1, so this has area 1/2, this part has area 1/2. So actually the total area forever, because there's a lot of 0 happening, of the convolution, f convolved with g, okay, we'll put the parenthesis here, dt, that is 1. And that's kind of a property of convolutions. If the area under f is 1 and the area under g is 1, the area of the convolution is 1. And in general, the area under the convolution is always going to be the product of the area of under each of these, as long as that area is finite. All right, here's something that a convolution can be used for outside of the context of a Laplace transform, and that's a dartboard. So if you look at this dartboard, there's different amounts of points for different places on the board. So there's different strategies you can use. For example, you might try to throw at 20, which might be a good strategy. That's the biggest number on the board. So if you get in this slice, that's really good. But it's surrounded by 5 and 1. So maybe don't throw at 20, because if you miss a little bit, that might be bad. You might throw maybe more at 16, because then if you miss, you're on 8 or 7. And if you miss a little more, you're on 11 or 19. Like this area might be a really good part of the dartboard. So there's two things going on with the dartboard. One is your strategy, and the other is your accuracy or your skill. I'm pretty bad, so I might like the distribution of where I land. Like, let's say I'm trying to target here. The probability of me landing here is actually not that high, and like I might be bad enough that I have some probability of even landing over here or completely off the dartboard. So depending on your skill, you have a probability distribution of where to land depending on where you target. That's just if you're trying to hit one point. And then you have a strategy, like maybe you try to hit here sometimes, or maybe you try to hit this region. And then, that's my dog barking. What ends up happening is the probability distribution of where you hit on the dartboard ends up being the convolution of your strategy and your skill. So you have a distribution for your skill. If you target one place, you have a distribution for where you might hit based on your strategy, and you do a sort of two-dimensional convolution of the two. And then you can kind of make you can look for these online. You can make a heat map of where you might hit on the dartboard based on those. I don't know what's happening with my dog today. So I thought that was a cool tie-in of convolutions to real life. And all of these, the Laplace transforms are used for things other than differential equations. The convolutions are used for things other than Laplace transforms. If you're interested in analysis, you might study Fourier analysis. Fourier transforms will also eventually bring up convolutions. There's a lot more to learn about all of these things and about differential equations, and if you're interested, partial differential equations. Not my specialty at all, but I know it's a really rich field. So you can think about going into that if you enjoyed this course.